All right, so this lesson is on forces of friction, and our goal by the end of this lesson is to be able to calculate the amount of friction an object is going to experience, and the way that we're going to do that is by identifying what factors affect friction. When I talk about factors, I'm going to be talking about things like size or mass or amount of force or even the nature of surfaces that are all factors that have an effect on friction. So that being said, before we get started doing any calculations, we need to have a really solid understanding of what friction even is. So friction is a force, but it's specifically a force that resists an object's change in motion. Making sure this erases. Oops, gotcha. Let's hit one more time. Perfect. So friction is a force that resists motion. So it's either a force that keeps things from moving, or while objects are in motion, it resists their movement in that direction. So friction is actually something that's caused at the particle level, the molecular level. We haven't really talked about particles in this class because that's more of a topic that you focus on in chemistry. But when we talk about friction, it is helpful to think about what's happening at the particular level. So I've got two books here, a chemistry book and a physics book. And I know that when those books rub one another, there is friction. We can see that as the motion between the chemistry book and the physics book increases, the particles increase their motion as well. And that increase in motion contributes to our friction, and it also contributes to temperature. So if you pay attention to the temperature dial on the right side, the more that the particles rub, the higher the temperature goes, and the more of a frictional force that there actually is. Eventually, you'll see a difference in the nature of the surfaces, which is why friction can sometimes smooth surfaces. This is how we'll sharpen knives actually, is through frictional forces smoothing surfaces and rubbing away particles that are in contact. But if I lift the books and I move them, they're not going to produce friction. They're not going to affect the particle motion unless they're in contact. It's the contact between the particles, their collisions, that cause them to move more frequently, which increases our heat. And that heat is what produces our friction as well. So when we look at it in this picture, we're not really looking at the particles, but we can see that even surfaces that appear smooth maybe aren't perfectly smooth. If you were to look at the micro level, you would see dips and divots and curves and edges and points that are going to get interlocked with one another. They're going to get stuck on one another, and they're going to produce forces when they come in contact with one another and they're pushed together. They're trying to slide past each other. I kind of think of it like the tectonic plates on the earth actually getting produced in contact with one another, pushing into one another, producing earthquakes. It's very similar to that, but on a micro level. So friction is something that is caused by those intermolecular attractions between particles on the two surfaces. So when they interact, the particles, when they interact, that's what we see as friction. We don't really see particles interacting, but we experience the heat and we experience the forces that resist our change in motion. So there are two types of friction. They both are produced by the interactions between molecules. However, one force of friction is the one that we experience when we're not moving yet. It's the friction that keeps us from moving at all. And that force of friction is called static friction. So the friction that keeps an object from moving is called static friction, which makes sense because static means that there's no change. So if you were trying to move a large object like maybe a table, and you gave an initial push and it wasn't hard enough and the table didn't move, didn't budge, The reason it didn't budge is because your force wasn't stronger or greater than the force of static friction that the table was experiencing. So the table stayed where it was. It stayed at rest, which is a static form of motion because it didn't change its motion at all. Kinetic friction is the force that same table would experience if you did push it enough to get it to slide. As it slides across the floor, if you were to keep pushing it, you would still experience friction, but it wouldn't be friction that's keeping the table from moving. It would be friction that is hindering the table's movement as it's sliding. And we call this kind of friction kinetic friction. So that's the friction you experience during any sort of sliding motion. And it makes sense that it would be called kinetic because kinetic is a scientific word for movement. So the friction you experience during motion is called kinetic friction, and the friction you experience while you're at rest is called static friction. So there are two factors that affect both static and kinetic friction. When we did our lab with friction moving coffee mugs, we added coffee beans. It actually wasn't coffee beans, it was pinto beans. But we added beans, in other words, added mass to our coffee cup to increase the friction that the coffee cup would experience. And the idea behind that is that if two objects are pressed together more tightly, they're going to experience more friction, kind of like the chemistry book and the physics book. When I lifted them apart and they were no longer in contact, there was no friction. And if I pressed them tightly together and I rubbed them, there was more friction produced between them versus if maybe they weren't pressed as tightly together. So the force that we're referring to when we're talking about how tightly objects are pressed together is the normal force. And normal force, by and large, is affected by the weight of an object or the mass of an object. So for example, if I have one physics book on my table and I try to move that physics book, I try to slide it, I'm going to experience the smallest amount of friction because there's a smaller normal force pushing up on the physics book. But if I were to add some mass on top of that physics book or to that physics book by adding several bricks, what's going to happen is that the table is going to have to exert a larger normal force to support that same physics book, which means I'm going to have more friction between the table and the physics book as they're being pressed together more tightly. And if I were to go a step further than adding just those bricks, if I were to press down on those two bricks, the table would have to exert an even larger normal force to support my hand and those bricks and the physics book, which would produce the greatest amount of friction between the table and the physics book. Because in this last situation, that physics book and the table are getting pressed the tightest together. So any sliding between them is going to produce the most molecular interaction versus when I have just the physics book. Yes, they're in contact, but they're not as tightly pressed together as they are when there are bricks and a force from a hand pressing that physics book down into that table. So normal force is a factor that always affects friction. The more normal force an object experiences, the more friction it's going to experience when it slides. Now, the second factor that affects friction is the nature of the surface. So we saw in our friction lab that when we taped surfaces to the bottom of our coffee mug, different friction was produced. And objects that were smoother, or surfaces that were smoother, experienced less friction than surfaces that were rougher. And that has to do with something called the coefficient of friction. Every surface, or I should say two surfaces that are interacting, experience a unique coefficient of friction. For example, if I were working on my table here at home, this is a smooth glass table, my phone is going to experience a coefficient of friction when I slide my phone across this table. But if I were to bring this table to my lab benches in my classroom, those lab benches aren't quite as smooth as my glass table, so my phone is going to experience a different coefficient of friction with that surface. That roughness is kind of like this picture that we've got of surface A and B. The more bumps and divots and crevices and points that two objects have, the higher amounts of friction they're going to experience. So in other words, the higher the coefficient of friction there's going to be. Versus if they were smoother, there's going to be a smaller coefficient of friction. So this table that we've got right here is just a table of example values for the coefficient of friction. So a car tire and asphalt experience a pretty high coefficient of friction together, which I guess is good because when you need to brake and stop, that's definitely a very necessary force. Friction is a very necessary force. But when you're looking at ice and how it interacts with steel or how it interacts with wood, the coefficient is very low, which explains why maybe ice skating is so effective. Versus looking at things like wet snow, these coefficients are still fairly low, but just not as low as ice. But you could definitely compare objects that maybe you can feel with your hands and notice a visible or a tangible smoothness. They typically have lower coefficients, whereas objects that you interact with your hands that tangibly feel rougher have a higher coefficient of friction. So these two factors we're going to put together to make an equation so that we can calculate friction for any circumstance in any situation. So let's look at those equations. So if we wanted to calculate how much kinetic friction an object is going to experience while it's sliding, the amount of kinetic friction is going to depend on two things: the normal force and the coefficient of friction, which is where I get my equation, my coefficient of friction times my normal force. The product of my coefficient, my normal force, is going to produce my kinetic friction, whereas my static friction equation is going to look actually very similar. Static friction can be calculated as well by taking the product of the coefficient of friction with the normal force. Now there is one key difference, and it has to do with the symbol in the equation. I'm going to highlight it to point it out. My kinetic friction is equal to the product of my coefficient and my normal force, but my static friction is less than or equal to the product of my coefficient and my normal. So that's a key difference there, and it has to do with this graph that we have here of static and kinetic friction. So there's a picture here on the bottom of someone pushing a block across a table, and they monitored the force that they pushed with as time went on in the experiment, and that force that they pushed with was always being balanced out by friction. So in the beginning, they pushed harder, all the way from 0 newtons to 40 newtons. And in this time, there was no movement. In other words, this force was all static friction. It was all balanced out by static friction, which means that the static friction amount changed. Its minimum was 0 newtons, right? And its maximum was 40 newtons. And if the hand pushed with any amount in between 0 and 40 newtons, static friction balanced it out equally. In other words, static friction could have been 30 newtons, or 20 newtons, or 10 newtons. It just hit a maximum of 40, which is why the static friction equation is less than or equal to. In other words, static friction can be any amount. It just has a maximum amount that it can reach. And it can be any value less than that maximum. Now, kinetic friction is a lot simpler because kinetic friction is this flat part of the graph right here. Once the block started moving, the amount of friction stayed constant, and in fact it dropped. So once the block started moving, it was easier to keep it moving, so to speak, because the amount of friction it experienced was less than the amount of friction it had to overcome to start moving. So kinetic friction is always a constant value, which is why we use the equal sign in the equation. There is no maximum amount, there is no minimum amount. It will always be only one value. Now, that being said, let's get practice using these two equations. So let's practice a kinetic friction problem and just get familiar with using the equation for kinetic friction. So the coefficient of kinetic friction between an 86 kilogram desk and the wood floor is 0.038. What force must be applied to move the desk at a constant speed? Now, what I'm going to do is very similar to what we've been doing with solving problems with Newton's laws. I'm going to list my knowns, and I'm going to list my unknowns. And this is going to help me with figuring out what equation I want to use or plugging into that equation. So they told me a couple of things. They told me that the mass of the desk is 86 kilograms. And they told me that the coefficient of kinetic friction, which is mu k, that's what this symbol is 0.38, and that's the only information they gave me. They didn't give me anything about the normal force or the friction force, or we can call it Fk for kinetic friction. Now, they're asking me what force must be applied to keep the desk at a constant speed. So that's kind of confusing because I don't know if that's going to be equal to friction or different from friction. So it might help to draw a force diagram. So my force diagram for my desk I know is going to have gravity. This is an unknown because they didn't give me the force of gravity acting on the desk. But I also know that there's going to be a normal force. And according to what they've described, it doesn't sound like my desk is accelerating upwards or downwards. It's not flying into the air, it's not flying into the earth or falling into the earth. So I'm going to assume that it's balanced vertically, that normal and gravity are balancing each other. Now, what they're describing in the question is that the desk is moving at a constant speed. So that means that it's moving either to the left or to the right, but regardless of direction, those forces are equal. So I'm going to just say it's moving to the right. That's not going to make a difference. I'm going to say this is just some applied force because I don't know if a person's pushing it or if it's being pulled by a rope. I don't know. So I'll just call it an applied force. And I know that that applied force is going to be equal to the friction force. So these two are going to balance each other out. So when they ask me what force is applied, that's the unknown I'm looking for. And if I could find my friction, that would be the same thing as my applied force. And I do have an equation for friction. So if I look up here at that equation, I'm going to write it over here. It's my kinetic friction equals my coefficient times my normal force. Perfect. Okay, so I do have my coefficient, but I don't have my normal force. That's an unknown. So I'm going to try and solve for my normal force by using my force diagram. So I know that my normal force is equal to the force of gravity, but they didn't give me that. However, I do know from my mass and weight equations that the force of gravity, or the weight of something, is equal to its mass in kilograms times 9.8. So I could calculate gravity, and by doing that, that's going to get me my normal force. So let's do that math down here. So my gravity is going to equal 86 kilograms times 9.8. Let's see. Do that in my calculator. Get out of here. 86 times 9.8. Perfect. 842.8 newtons. So if my gravity is that many newtons, and it's balanced with my normal, that must mean my normal is also 842.8 newtons. So now I do have normal, and I can plug that into my friction equation. So I'm going to do that math right here. So my force of kinetic friction is going to be equal to the coefficient, which is 0.38, times my normal, which is 842.8. Now, I don't know why I put parentheses around there. Sometimes I do it because I want to keep my work organized. It didn't really make it all that organized, but it didn't make a difference in my problem either. So I just need to multiply 0.38 times this number. So let's multiply by 0.38. And I get 320. Let's just round that to the 10th place, 0.3 newtons. 320.3 newtons. Wait, did I get that right? Yeah, I did. Okay, so if this is my friction, then that must mean my applied force is the same thing, because those two forces are balanced with each other. So I guess I've got my answer to the question. What force must be applied to move the desk? That's my applied force. I just solved for that at a constant speed. Perfect. I'll just write it down and box my answer. My applied force is 320.3 newtons. Awesome. Okay, so that was one problem using kinetic friction. Let's do another problem using static friction. So the coefficient of static friction between an 86 kilogram desk and the wood floor is 0.45. What force must be applied to get the desk to start moving? So I'm going to approach this the same way that I did my last problem, by listing what I know and listing what I don't know. And I'm going to be prepared to draw a force diagram, just like I did last time. So again, my mass is 86 kilograms, and my coefficient of static friction this time is 0.45. Perfect. Okay, and then my unknowns, there's quite a bit. They asked me to find the force applied to get the desk to start moving. So I'm definitely looking for an applied force here. They didn't give me normal force, which is something that I'm going to need for my equation. They didn't give me my weight, my force of gravity, and they did not give me my force of static friction, obviously. So I'm going to draw a force diagram. I think that'll help me organize my thoughts a little bit more, because I'm still not quite sure where to go from here. So I know that the desk is going to experience gravity, and I know that it's also going to experience a normal force. And since it's not accelerating up or falling into the earth, I'm going to assume that these are balanced. And I know that the desk it's starting to move, which means it's accelerating forward horizontally. So I know that this applied force is going to be a little bit greater, or at least greater, than my static friction. As long as it's greater than my static friction, it should be enough to get the desk moving. If it's equal to my static friction, then it's not going to move at all. And I don't want that to happen. I want it to start moving. So now I've got a nice diagram. Let's see if I can maybe start solving for some things. So right off the bat, let me write down my friction equation and see if maybe I can solve for friction right away. So I know that my equation for static friction is this. I know my coefficient, but I don't know normal, which means I need to find my normal force. So my normal force is equal to gravity. If I could find gravity again, then I could find my normal force. So let's do that. So mass, this is actually going to work out very nicely because my mass is the same mass as the last problem. So this is going to be 86 times 9.8 all over again, which I already know the answer to that from the last example. So my force of gravity is again 842.8 newtons, which means my normal force is 842.8 newtons. Perfect. So now I know normal. I can plug that in to my equation. So my static friction is any value less than or equal to 0.45 times 842.8. So let's go back to the calculator. 842.8 times 0.45 gets us 379.26. So static friction is any value less than, I forgot for a second, 379.26 newtons. So it could be 0, it could be 10, it could be 200, it could be 250, it could be 378, it could be 378.9, it can be any value that's less than 379.26, and it can be 379.26. So if I assumed that this was at the maximum, 379.26 newtons, my applied force would just have to be a number greater than my static friction to get it to start moving. So it could be 380, it could be 400, it could be 1,000, it could be anything as long as it's greater than my static friction. So instead of giving a number, I'm just going to give a statement. Applied force would just have to be greater than 379.26 newtons. So that's mathematically how I could write that, or I could use words and just say applied force would be greater than 379.26 newtons. So as long as you're going through these problems and following this process of step 1, figuring out what you know and what you don't know, step 2, drawing a force diagram, and then step 3, determining what equations you need and plugging in, you should be good to go. So that concludes our lesson on the force of friction. Hopefully you've got enough experience now to start practicing calculating the amounts of friction that objects experience.